All right. Today's goal is to come up with derivatives of inverse trig functions. So I'm gonna show you the derivation of them, and like the other day when we did logs and e to the and a to the and log base a's, I showed you where they come from, but you don't have to spend a lot of time working on that derivation. You don't need to memorize those derivations. Really, you need to start memorizing the rules. So I'll talk about that as we go here too, but our goal is to come up with some rules for derivatives for inverse sine, inverse cos, inverse tan, and so on from there. We might even do some secants and cosecants, but that we'll see. We'll see if we get there. And we're gonna talk, and this is that second piece is a little bit more tomorrow, but it's really important here to note that there's a very special relationship when we're dealing with inverses and graphs and slopes, and that's probably going to come more into play tomorrow. We went through that warm up. Let's go to this. I don't think this question isn't stated how I wanted to say it, but really we want to ask the question: how is inverse secant related to inverse cos? And I'm not really expecting you to come up with this on your own, but I think hopefully as we do this, it'll make sense. The question would be, and you're used to trig identities, and the goal here is how can you turn inverse secant into inverse cos, and what does that do to the angle? So let's go through this. We're going to start with secant inverse. So secant inverse of x is equal to some angle theta. Knowing that when we're doing secant inverses, we're doing trig inverses, we're given a ratio value, and we want to know the angle. So x would be the ratio, theta would be the angle. That's a true statement for what we're dealing with secant inverse. What's another way of writing secant inverse of x equals theta? Think inverse. Great. Secant theta equals x. That fair so far? Okay. That's true, right? That's by definition of inverse. Those two things are the same, right? What's another way to write secant? 1 over cos. So this is 1 over cos theta is equal to x. Okay, we haven't done anything earth-shattering yet, have we? We used some basic properties of trig, right? And some definitions. Okay? Let's take that and solve it for cos theta. Because our goal, keeping in mind, remember all these trig identities you had to prove last year? We're going to start with secant inverse, and we want to get to cosine inverse. Okay? So let's solve 1 over cos theta equals x for cos theta. What do we get? Cos theta equals 1 over x. Just take a moment in your mind and defend that. Good so far? Are we almost to a point where we can write it in terms of a cos inverse? What would the cos inverse statement here be? Cos inverse 1 over x equals theta. But wait, go back to the beginning. What was theta? Secant inverse, right? So the question, what is the relationship between secant inverse and cosine inverse? Is this: secant inverse of x is equal to cosine inverse of the reciprocal of that. And I think it's significant. We're not going to dig into it a lot today, but I think that's an important relationship. The inverse of a secant is the same as the inverse of the cosine of the reciprocal of what we put in originally. I don't know. Is it something that you need to know? It's something that's pretty nice. Okay. I think it's helpful, especially when we get to this example. What's secant inverse of 2? What's another way of writing secant inverse of 2 based on the result we just came to? That's the same as inverse cos of 1/2, right? Based on the previous result, you know inverse cos of 1/2? Angle whose cos is 1/2. We got a trig ratio. Let's draw a triangle. Cosine is adjacent hypotenuse. What angle is that? The pi over 6, pi over 3. That's pi over 3, right? Pi over 3. Okay. Is that something that's going to change your world? I don't think so. But trig is about patterns and relationships, and I think that's kind of a cool one. I think that helps. Good so far. Do you ever have to re-justify this verification? Probably not. Next little result to be able to play with, though. All right? All right. 4 useful identities. These are useful in the context that we're about to use them in finding derivatives of inverse trig. So take a look here. There was one of these on the bottom of yesterday's worksheet, right? Did you get it? Feel good about it? We want the sine of the angle whose cosine is x. I've got triangles over there for you. Let's label an angle. Let's call this theta. Okay? What's the easiest way to label this triangle so that its cosine is x? Cosine of theta is x. Where should I put the x? On the adjacent side. What else do I need to label if I'm going to make that assumption? Hypotenuse is 1. What do I have to do now? Solve for what? Solve for sine? Kind of. We could, well, we want sine. You're right in that we want sine. What is sine on that triangle? Isn't that this right here? Isn't that sine theta? That side length? How do I find that side length with the assumption that that's a right angle? I drew them that way on purpose. What should I use? Pythagorean theorem. So what is that sine value going to be? 1 minus x squared underneath the square root, right? Because sine squared plus x squared equals 1 squared. Good so far? We try these next two. Are there 4 of them? There's 4 of them. Try the next two. All right. Many of you did a nice job here so far. With cosine sine inverse, we ended up with the same thing again, 1 minus x squared underneath the square root, and we got that from these labels. We okay with that one? Next one, secant of inverse tan. I ended up with this. Square root of x squared plus 1. Remembering that tan is opposite over adjacent, these labels become x and 1, if that's theta. And then we end up with, is that right? Is that what you guys got? We end up with that, x squared plus 1. Okay. And then secant is 1 over cos, right? 1 over cos. So cos is 1 over this root, and 1 over a root is just the root. We good? Let's get this out of the way. Last one, what'd you get? The frustrating thing about these is they all look really similar, which makes them really hard to memorize. And I don't think you need to spend a lot of time at this point memorizing those things. You're going to need to memorize what's next, because we're going to do some derivatives. We're going to do some differentiating, if you will. Question? Yeah? One more time. When I have this, well, I guess the way I reasoned through it is I said that secant is 1 over cos, and cos is adjacent over hypotenuse, so it ends up being 1 over the square root of x squared plus 1. And I don't know, there's probably other ways to think about it, but I've got 1 over, and I just multiply top and bottom by the root, and I end up with that. That kind of, there's other ways of thinking about it, but you thought of it as secant is secant theta is hypotenuse over adjacent. Yeah, that's fine. That works too. Yeah, a couple of different ways of looking at it. You can probably do the same thing on the last one. Yep. Great. Great. Yeah, there's other ways of looking at it. This is the way it makes sense to me. That's the beauty of this, though. It makes sense to different people in different ways. Okay? That's really important because we're about to turn the page. We want to find derivatives of inverse trig functions. Now, this is going to be a lot of, this is that concept stuff. This is the derivation of some of these inverse trig rules. Do you need to memorize how to get there? No. But it's really good to have a defense of why it works. So put this in your notes and work with me as we go here. We're going to use the idea of an inverse, and we're going to use implicit derivatives in order to come up with a derivative of inverse sine and inverse tan. You ready? No? Yes? Okay, so let's go sine inverse x. I'm going to say that sine inverse x equals y. Because whenever we're doing derivatives, it's nice to have an x and a y. Also because we're about to do some things with implicits. What's another way of writing sine inverse x equals y? Sine y equals x. Good so far? Okay, now we'll do an implicit derivative. On both sides, I will differentiate with respect to x. What is the derivative with respect to x of sine y? Cos y times dy dx, or y prime. dy dx. You can call it y prime if you'd like. What's the derivative of x? 1. Great. Okay. Good so far? How do we solve for dy dx? Divide by cos. So dy dx, the derivative, is equal to 1 over cos y. We good there? Done? We're not done. What do we need to do? Substitute for y, right? So dy dx is equal to 1 over the cosine of, what's y again? Sine inverse. Gosh, you know why we did that last page? Now, honestly, I don't know how often this is going to be useful in your life, but go back to the last page and find out what the answer to that was. What is cosine of sine inverse of x? Now, there's your derivative. If the function you're given is sine inverse x, the derivative is 1 over the square root of 1 minus x squared. Okay? This is the perfect example of making prerequisite knowledge apply in the here and now. Like, you used what we did on the previous page to show that we can come up with a rule. Now, do you ever need to do that derivation again, guys? Probably not. But you now have a defense. We used implicit derivatives and the definition of an inverse trig function to come up with a derivative for sine inverse. Okay, question? Good? Okay, let's do the same thing with tan. Let's go tan inverse. Okay? What's another way to write tan? Well, let's do this. Tan inverse x equals y. We need another variable there. Okay, so let's go tan inverse x equals y. You could use theta. Doesn't matter that much. Some people would use theta because the theta is more fun with trig functions, but we'll just make it y for now. What's another way of writing it? Tan y equals x. Let's differentiate. Derivative on both sides. What's the derivative of tan? Secant squared y dy dx equals 1, right? How do we solve for dy dx? Divide by secant squared y. So dy dx is equal to 1 over secant squared y. Where do you suppose you're going to go? To the previous page. So we're going to change the y to, well, actually, you know what? We got to change the y back before we go back to the previous page. So this is dy dx is equal to 1 over secant squared of inverse tan inverse of x. Now you're going to go to the previous page in the notes. What is secant of inverse tan? 1 over, keep in mind that this secant squared is taking the secant then squaring it, right? So it's 1 over the square of secant inverse tan, and this is this thing, right? Good from the previous page? So the derivative of tan inverse is 1 over x squared plus 1. Your derivative for inverse tan. Isn't that fun? I'm sorry? Question. Is there a question or are we good? Question. Isn't 1 over secant squared cosine squared? Yes, it is. But if you wrote it as this, we wouldn't be able to use a property that we learned on the previous page for it. Now you could go through that if you wanted to. I'm willing to bet. I'm willing to bet if you drew the triangle, it would work out the same. I don't want to do it today, but you can convince yourself by drawing the triangle and doing cosine squared of inverse tan. I bet you get 1 over x squared plus 1. I don't bet though. I'm not betting. If I were though, I'd bet on it. Good observation on that though too. Yes. Secant squared is 1 over cosine squared. Another question. Are these methods improving? Well, this is what we would call a derivation. We are deriving. I'm showing you the why the rule is what it is. Now, moving forward, and as soon as this lesson is done, you don't need to do the derivation. You just need to memorize the rule. And worst case scenario, if you had time and you had to do that derivative, you probably could come up with a strategy to do it. If you have to do it that way, no. I think it's easier to memorize the rule. Does that answer your question? So what I've basically done is I've shown you that the derivative of sine inverse is 1 over root 1 minus x squared. And the derivative of tan inverse is 1 over x squared plus 1. Good so far. You would use a similar method for cosine. We're not going to do cosine today. You'd use a similar method though. Okay? So using those ideas, we now will bring in chain rule. You ready? We'll now bring in chain rule. It's a composition. The outside function is the same. We want the derivative of sine inverse. Okay, but we're going to do sine inverse of a function of x rather than sine inverse of x. So using that idea from the previous example on sine inverse, we said that this was our derivative, wasn't it? 1 minus x squared, right? What if that x gets replaced with f of x? What do we do? Change x to f of x. So the derivative of sine inverse of f of x would be 1 over square root 1 minus f of x squared. But since I had a function on the inside, what else do I need to do? Find the derivative and multiply by it. Okay. We'll do a couple actual examples here in a moment. But okay? We did that with logs in each of those, right? It's chain rule. If I've got sine inverse of a function, the derivative is the function in place of the x's, and I multiply by the derivative of f because it's the inside function. Okay? Tan inverse. What's the derivative of tan inverse? We write it down? I like to simplify this one too, guys. I don't know if you do or not, but I like to simplify this. I don't know. I think it looks cleaner. Doesn't really change your world any, but I like to write it like that. Okay? Inverse tan. What would you write? One over x squared plus 1, right? What goes in for x? F of x. What do we multiply by? the derivative of the Tootsie Roll center, right? Chain rule. So I would write it like this: f prime of x divided by f of x squared plus 1. Okay? And that's all symbols. Should we actually do a couple examples now? Ready? Ready? All right. I'll show you the first one. I'll have you try the second and the third. Let's start with A. Let's start with A. We want the derivative of sine inverse of x squared. Okay? The outside function is sine inverse, so I'm going to start with the framework for sine inverse. What's the derivative of sine inverse? 1 over square root 1 minus x squared, isn't it? 1 minus x squared. But I like to leave parentheses because I'm not putting in x. What am I putting in? I'm putting in x squared. And because x squared is a function, I need to multiply by its derivative. And the derivative of x squared is 2x. So I would write this answer as 2x divided by the square root of 1 minus x to the 4th. How's that? Not terrible as long as you can memorize that rule. Trick is finding a way to memorize that rule. Okay? You need to memorize 6 of them. Well, it's really 3 of them. Sine, cos, and tan really is all you need. Sine, cos, and tan. We'll do it at the back in a minute. We'll summarize it all and wrap it all together. Okay? What about B? Will you try B? Do B on your own. And if you're really, really adventurous, do C, and we'll talk in a second. With the sine inverse 3x plus 1, I think it's worth reminding yourself that this is f prime of x over the square root of 1 minus f of x squared, and then keeping in mind that 3x minus 1 is f of x. So f prime of x, if x is 3x minus 1, is 3. On the bottom, then, we have the square root of 1 minus quantity 3x minus 1 squared. And I don't think it's worth foiling. I think you need to be careful if you do it. I think this is sufficient for our derivative for that one. Okay. One place we're getting caught up a little bit, and this is part C. It's actually a little more of a complicated composition than some of you are seeing. So let's walk through it. The framework for tan inverse is 1 over f of x squared plus 1, isn't it? Is that the tan one? Okay. We need f prime up here because we had a composition. That's f prime of x. Now, what I might do here is I might say that f of x is equal to x plus 1 to the 1/2 power. That's a square root function for f. And we need to write out f prime. If that's f of x, we got chain rule here. F prime of x is 1/2. Leave the inside the same to the negative 1/2 times the derivative of the inside. What goes in here in parentheses? X plus 1. What goes out here is the derivative of x plus 1. 1. Okay? Question. The bottom wouldn't be squared on the tan one or the sine one? Well, why isn't there a square root over the bottom of the tan? It goes back to this derivation back here that we ended up with secant squared, and when we squared the square root result, we ended up with, so if we square that square root and the root's gone, that's why we don't have a square on it. Kind of goes back to that derivation. Does that help a little? Okay. Then, I mean, it makes that one a little easier to memorize because when you get to tan inverse, you know there's no root. Sine has a root. Cos has a root. We haven't done cos yet, but I'll show it to you in a minute. Okay. Should I keep going on this one? So we end up with 1/2 x plus 1 to the negative 1/2 all over square root x plus 1 squared plus 1. I simplified that denominator is actually x plus 2. So I have an x plus 2 on the bottom. I put the 1/2, I take the 2 from the bottom and put that on. And I also have a negative exponent on an x plus 1. So I ended up with this as my final answer. I don't think all that simplification is required, but that's where you would end up. Questions on that? Okay. Should we do one little application problem? This will take us back a little bit. We've got a particle, moves along the x-axis, so its position is given by an inverse tan of the square root of t. What is the velocity when t is 16? So we want x prime of 16. First thing we need is x prime. What's the derivative of tan inverse? It's 1 over x squared plus 1, right? Let's memorize that one soon, okay? Find a way. You can probably come up with better ways than I can. But this, since it's a composition, the top is f of x, the bottom is f of x, or this is f prime of x, sorry, f prime on the top, okay? What's the derivative of the square root of t? 1/2 t to the negative 1/2. Does that look good? This bottom part's the square root of t squared. I'll write it as t, put a plus 1. Good so far? Do we need to simplify? What are we going to put in? 16. So x prime of 16 is 1/2 times 16 to the negative 1/2 over 17, right? 16 plus 1. Good? Okay, 16 to the negative 1/2 is a square root and a flip, right? So the top ends up being 1 over 8. Double check and make sure that seems about right. 1/8 divided by 17. You don't need your calculator for this at this point, but I'll give it to you. It's 1 over 136. Okay, that's what an application might look like for an inverse trig derivative. Okay. Let's wrap this up. These are the rules that you're going to need to find a way to memorize. Ready? Inverse sine, if it's just x, inverse sine is 1 over square root 1 minus x squared. Yeah? We derived that one. What's cool, if you start with sine, the cosine one is easy. You can do, I'd like you to consider trying to do this derivation on your own, but I think it's kind of cool that and again, I think way too much stuff is cool these days, guys, but the derivative of inverse cos, I think you should derive it, but the derivative of inverse cos is just the opposite of the derivative of inverse sine. You might need to convince yourself of that one. That doesn't seem right, does it? It does seem right. Some of you are convinced. It seems right. Play with it. You might even find something in your notes that would allow you to convince yourself of it. Okay? We did the derivative of inverse tan. That was 1 over x squared plus 1. Find a way to put that into your brain. I don't know. I don't have a song for you guys. I wish I did. I wish I had a song for derivatives of inverse trigs, but there's nothing that rhymes with inverse trig. So I can't make up a song for you. All right. Then when we put in the composition piece, we have f prime of x on the top, and then on the bottom we end up with the square root 1 minus f of x squared. Same thing with the cos, except the cos has a negative sign in front of it. Those of you that are so easily convinced that, of course, it's the opposite of that one. I'd love to hear from you. That's f of x squared on the bottom. Derivative of inverse tan. We did this as 1. Actually, we did it as f prime of x over f of x squared plus 1. All right? Your homework is listed on your sheet as day 2. It's listed as 3.10 day 2. And I would not like you to do all of it. I would like you to stop after problem 35. And 35 is a little bit of a trick too, but stop after problem 35 because the rest of it involves a cool little inverse trick I'm going to show you tomorrow. And I really hope it makes a lot of sense.